Okay, in this lecture, we'll continue with our section 2.5 material on physical applications of the integral. And here we'll start talking about the concept of work. So let's introduce the idea of work, or if you've had some elementary physics, this will be a little bit of a review. So in physics, work is related to force, which is intuitively defined as a push or a pull on some object. So when a force moves an object, we say that that force does work on the object. So in other words, we can think about work as the amount of energy it takes to move an object some distance. Now, in the case of a constant force, F, the work, which we will denote as W, done in moving an object a distance d, is given by the following equation. So work would be defined as the product of force times distance. So the magnitude of the force, how strong this push or pull was, times d, the distance that we've moved our object. Of course, the longer or the further distance that you would move an object, the more work would be done. So let's consider a simple example in calculating work, and then we'll consider the case that our force is not constant. So in this first example, we are asked how much work is done by a weightlifter in raising a 60 kilogram barbell from the floor to a height of 2 meters. So using our basic formula for work, we know that work is given as the product of force times distance. And in this problem, we're told the distance that this weightlifter is lifting the barbell is from the floor to a height of 2 meters. So we're given our distance as 2 meters. But what's a little tricky here is that we're not quite given force. We're given that this barbell is 60 kilograms, but this is a unit of mass, not force. So let's think about how we could get force from mass. Now, making use of Newton's second law, force is given by the product of mass and acceleration. That is, force is mass times acceleration. And then to get work, we're taking force and multiplying by the distance over which our object is moved. So let's see what we have here. We would have our mass of this barbell is 60 kilograms times acceleration. Now, what acceleration are we referring to here? Well, it would be the acceleration that we need to overcome in order to lift this barbell. So that would be the acceleration due to gravity acting downward on this object. And the magnitude of that acceleration is given by approximately 9.8 meters per second, or meters per second squared, times the distance that this object is moved, which was 2 meters. So taking the product of these quantities, 60 times 9.8 times 2, we're left with 1176. And here, let's think about what our unit would be. So when we're taking the product of a kilogram times a meter per second squared, that's a unit that we call a Newton. It's a unit for force. And then we're multiplying by a distance in meters. So we could say 1176 Newton meters, or this is sometimes also referred to as a joule. So in which case we could write, instead of Newton meters, we would write a capital J for a unit of joule, or joules for work. So of course, either of these would be an appropriate unit here. Now, in the formula that we've reviewed for work, for basic physics, we said that this formula holds in the case that we have a constant force F being applied to our object over this distance d that we're moving it. However, of course, not every force is constant as we're moving an object. So we can think about, well, let's say we were trying to push a heavy box up some ramp or along the floor over a long distance. Well, we might not always be able to exert the same amount of force over that interval. We might get a little more tired at certain points and not be able to exert as strong of a force on our object as we're moving it. So what we'll start to consider is what would be the work done by a force which is varying as we're moving an object along some line. So the following theorem gives us a way to calculate the work done by a variable force. So let's suppose that we are interested in the work done by some variable force, let's call it f of x, in moving an object along the positive x-axis from x equals a to x equals b. So I claim that the work done by this variable force f of x in moving an object from point A to point B is the definite integral of that force function with respect to x over the interval from A to B. Now let's think about why this might hold intuitively. So if we have our x-axis and we have some object which we're moving from a point x equals a up to a point x equals b, and we want to know what is the work done by that force as we're moving along this line segment or along this path. Well, we can think about dividing up our path of motion from point A to point B into small subintervals of length dx taken at a distance of x units along the x-axis, where x could range from A to B, and at any one of, or over any one of these small intervals, dx, the magnitude of our force would be given by f of x. So as x changes, the magnitude of our force, that is the strength of our push or pull, might be changing. And to find the work done by this force, f of x, as we move over that very small interval dx, well, we would take the product of this forcing function, f of x, times the distance that we moved it, which we would call dx. And then we want to add the work done over each of these small intervals, which was given by f of x dx. And we want to add those up over the entire length of our interval from point A to point B. So that process of adding up these quantities over very small intervals over some x interval is given by a definite integral. And here we're integrating from x equals a to b. So we're adding up the work done on each of these small little intervals as x ranges from a to b, and that would give us the total work done by this variable force in moving the object along that line. So let's consider an example of this. In our next problem, we're told a particle is moved along the x-axis by a force which is variable. So at any point x, the magnitude of our force is given by f of x, which is 5x squared plus 1 pounds. So the farther that we're moving our object along the x-axis, that is, the larger that x is, the larger the magnitude of our force. And it says at a point x feet from the origin. So we're supposed to find the work done in moving this particle from the origin to a distance of 10 feet along the x-axis. So using our new theorem for the work done by a variable force, well, we would be integrating here from x equals 0, since we were told that we're moving the particle from the origin, so that would correspond to an x value of 0, to a distance of 10 feet from the origin, where x would be 10. So here our integral will range from 0 to 10, and we're integrating our force function, which was given as 5x squared plus 1 pounds times dx feet. So here, finding our antiderivative, we have a 5/3 x cubed plus x, which is being evaluated from 0 to 10. So let's see what we have. When we evaluate at x equals 10, we have a 5/3 times 10 cubed, or 1,000, plus 10, and then we subtract what we get when we evaluate at 0, which would be 0. So here we have 5,000 thirds plus 10, or if we get a common denominator, we would have 5,030 thirds. And let's think about what our unit is here. So here, the magnitude of our force was in pounds, and the distance that we were moving along was measured in feet. So for work, taking the product of a force times a distance, we would have foot-pounds. Or if we want to maybe approximate this, instead of giving it as 50/30 thirds, this is approximately 1,677 foot-pounds. So here we would have our exact answer, or if we round this to, say, the nearest integer, we would have 1,677 foot-pounds. So something I'll mention when we're looking at these couple of problems, in the case that talking about units, in the case that force is measured in newtons and distance is measured in meters, then our unit for work would be Newton meters or joules. And in the case that our force is being measured in pounds and our distance is in feet, our unit for work would be foot-pounds. So something to keep in mind throughout this section.